It's a very cryptic title. It's a very technical paper. It's also a short paper, so like a short, very cryptic technical paper. Given this, I'm packaging it into some kind of more lightweight story, and I keep the whole presentation fairly lightweight. So we're looking at the marriage, okay, of two entities, let's say. I'm first going to talk about the world in which the story takes place and so forth, how marriages go. Now, of course, it is clear to me that you didn't understand this. You can look down here for a somewhat more concrete description of what the paper is about. We're going to make a crossover of delete relaxation and critical path heuristics. Now, first, what is the context? Strips land. You all know this land very well. I don't think I have to explain it. The only thing I'd like to point out is this regression notation here. Okay. So it's the usual strips regression notation, nothing to worry about. The one thing you should remember is that when I say capital R, what I mean is strips regression. And when I say capital R equals bottom, I mean that, well, we can't regress this goal over that action. Okay, otherwise, it's what you're used to. You have to add one goal. You don't delete any of the other goals. Okay. Good. The world is populated by the usual suspects. Okay. This one here is one thing I simplify just to avoid too much clutter on the slide. So basically identify a heuristic. When I say heuristic, I just mean its value on the initial state. It's very easy to generalize to all other states, but we just consider this as a slide simplification. And when I say something like that, I mean I compute the same heuristic but on a different planning task. Okay, now here's what we're actually talking about. I'm calling it the man-in-the-middle marriage because actually critical paths HM and H+ have already been married quite a few years ago now, 3 years back. But Patrick Haslam, the thing is this marriage actually has a man in the middle, namely a compilation. Okay, so we didn't combine the two things directly, rather we made a compilation that sits in the middle and combines them. This slide here very briefly explains the compilation, and you don't need to understand all details. I'm going to illustrate with a small example. In any case, the idea is that you select a set, capital C, of conjunctions, and you make them explicit in the planning task. And then the delete relaxation has to deal with those conjunctions in a more informed way than it usually does. This here is just a notation, okay? It's saying that if you have a set X of facts, then X to the C is the same set of facts plus new fluents, pi fluents that we introduced to represent the conjunctions. So this here is a pi fluent which says if I'm true, then that means that this conjunction here has been achieved like together, all together at the same point, rather than usually delete relaxation can actually achieve all the facts in the conjunction separately. Now, here's the actual definition. You're given the planning task, okay? Facts, actions, initial state, goal. For facts, initial state, and goal, you just insert the pi fluents and you're done. For the actions, it's a bit more complicated. What this here is saying is that for every action and for every subset of conjunctions that this action might make true, I'm introducing a new compiled action. Okay? I'm taking all combinations of actions and conjunction sets that can be made true thanks to the action. What does it mean to make a conjunction set true? Well, for each conjunction, you have to add part of the conjunction and delete none of it. And that's where the delete information comes into play. Okay, we can only add this pi fluent if we delete no part of the conjunction. You have to add some part of the conjunction, and the part that you don't add goes into the precondition of the compiled action. Because that already has to be true beforehand, so that, thanks to applying the action, the whole conjunction becomes true. Now this here is just combining this for all conjunctions we are throwing at this particular action. I'm using singleton conjunctions, which means that everything is a conjunction and the effect of the action is just those pi fluents. Nothing to worry about. Okay, what's interesting about this is that there's always a set of conjunctions so that the heuristic actually becomes perfect. Okay, so this is a way to interpolate all the way between H+ and H star, which is quite nice. The downside, which perhaps already is obvious to you, is that the size of this compilation is actually exponential in the number of conjunctions, because here I'm enumerating subsets of conjunctions. Okay, so it's going to blow up very quickly, at least in the worst case. Now here's an example. So I'm keeping this very simple. We have a goal A and B. Okay, but each of our actions achieves one and deletes the others. So the goal is impossible to achieve. Yet we all know that delete relaxation is not going to notice. H+ is going to be 2. Now if I introduce just a single conjunction A and B, what's going to happen? Well, that conjunction is going to be in the goal, right? Because our goal contains both the singleton facts A and B. So we add the pi fluent pi a and b into the goal in the compile task. Now, is this compiled goal achievable under the delete relaxation? Does somebody see? Aris is shaking his head, and that's correct. The answer is no, because there's no action achieving that pi fluent, right? We only got 2 actions to choose from. Each of them deletes one part of the conjunction, so in the compilation I won't actually include any action that achieves that pi fluent. Therefore, H plus is infinity. So actually, H plus in this case became from very bad to perfect by adding just a single conjunction. Usually in practice it's not that easy. You need big conjunction sets to achieve something. In any case, so this is like the background. Now, what this paper here does is basically do the same thing, but without the compilation. And thanks to that, we'll be able to actually get a heuristic that achieves basically the same information, but without the exponential blowup. Okay. So I'm basically defining an equivalent heuristic that doesn't have the exponential blowup in the middle because I'm getting rid of the compilation. Okay. Now I've already presented to you the bright people, or whatever they're called in English. Actually, I'm going to use slight modifications which will make the combination very obvious. So this here is very simple. I'm just rephrasing HM to HC. Okay, so this is a new notation. It hasn't been in the literature anywhere, but it's really completely straightforward. Like, there's no need to collect all size M conjunctions. There's no need whatsoever. You can just fix a set of conjunctions. And then instead of down here, as we usually do in this equation, select all size M subsets, we just select all subsets that are contained in our conjunction set. Okay, other than that, it's exactly the same thing that you already know. Good. The other side is a bit more interesting. So I'm doing this based on an equation formulation. So I also have to formulate H plus as an equation. Now this equation here is quite simple. I'm not sure if you agree yet, but if you have a little look through this, I mean, you know, the goal is already true. It's 0. Otherwise, we just take some action that adds part of our goal, and note we don't have to care about the delete effects, right? And then we just subtract what we already achieved and include the precondition, and we continue. So it's not hard to see that this is H plus. Now this one here is a bit more confusing if you look at it at first sight. And it's just an awkward reformulation which makes no sense in this particular case, but it's really the basis from which you can extend this to handle conjunctions. And really the dimension along which we extend this is the role that single facts play in all what we usually do, hFF, H plus, H max, you name it, is now taken by conjunctions. So whereas previously you had a single fact, now you have a conjunction. And anyway, I'm sort of getting ahead of myself. All I'm writing on the slide is that you can formulate a delete relaxation as taking the set of subgoal facts you have at the moment, just splitting it up into its single elements and applying the regression onto each of those elements. That's all I'm saying here, right? I'm just taking each single fact P. I'm saying I can regress this over the action, which is a very simple special case because if your goal is a single fact and you have to add it, well, then you're not simultaneously deleting it. So this, for singleton facts, regression is actually delete relaxed. And thanks to this observation, we can formulate the delete relaxation as considering, you know, you have a subgoal, you just split it up into its single facts, and you regress over each of those individually, but you use the actual definition of regression. Not a relaxed version, though, the actual definition of regression. And now, here's how it goes. Rather than doing it this way, which is what I just explained, I do it that way. I do exactly the same thing, just whereas previously I took single facts, now I take the conjunctions contained in my subgoal. And I have to regress over each conjunction separately. Okay. So here's the equation. I'm saying down here it's a direct generalization. To me, I've been looking at this equation for a while. It has become kind of obvious. Do understand? It's not that easy at first sight, but good. Okay. Instead of speaking over of a set G of facts, now we speak of a set like capital, big, whatever G of conjunctions. But that's really it. I mean, it's just a set of conjunctions rather than facts. Now, look at the bottom case first. Here I just collect for every conjunction in my subgoal all subconjunctions, and I put them into one big set. So this is like the splitting up step in critical path heuristics. I just select all subgoals that I care about. Okay. Then in the second case, I actually achieve them. How do I do that? Well, exactly like on the previous slide. I just look at each conjunction subgoal separately. I try to regress it, okay, here. And then I forward to the next call of this, like the union subgoal. The only thing that really is substantially different here from before is this symbol here. Okay. it is no longer possible to always select the largest possible set of sub-goals. You actually have to make a selection. Selecting more sub-goals can be detrimental. Even though your action can actually add them, it can be detrimental to add all of them. And if I can just postpone this for a little bit, I'm going to explain in a moment why. Yeah. For the moment, I'd like to give you sort of the certificate. So is this really a marriage? Well, this here is like the central theorem of this part, if you will. It's just saying what I just told you is exactly equivalent to what Patrick told you 3 years ago already. So it's doing the same thing, and that's actually a feature, because that's what I wanted to achieve. I want to do the same thing, but without a compilation. Now, from known results, it follows that you have all the properties you'd like to have, like the marriage dominates each of its components. It's a perfect marriage if you choose the correct set of conjunctions. And I have no idea how to phrase this in terms of real-life marriages, but you also have the same thing like in the what we all usually do, like H1 or H max is infinity if and only if H plus is infinity. So like relaxed plan existence is still governed entirely by the critical paths part of the marriage. Okay. Now all of this is just, basically following from known results. Now, this last part that I said is interesting, and that's where it gets practical. Okay. So I said to you that whatever H1 is for H plus, HC is for HC plus. Now, we already know about this infinity thing, but you also all know what we do if H1 is not infinity, we extract a relaxed plan, right? I mean, at least some of us do, if we do satisficing planning. Now, we can do exactly the same thing here, okay? So now, instead of extracting a relaxed plan from H1, I'm extracting a C relaxed plan from HC, and like at an abstract level, the only difference is rather than I'm considering single fact subgoals, I consider conjunction subgoals. In any case, let's briefly read this. I compute HC up front, like we usually compute H max up front, or H1. This here is just sort of the most costly goal layer, as usual. Then we proceed from the goal layer to the initial layer, as usual. I mean, think of this like a relaxed planning graph that reasons over conjunctions. Okay, okay, that seems to have made it clearer. Okay, so, I mean, we're just doing the usual thing, really. This is just collecting the sequence of our relaxed plan actions. Now, here's somewhat of a difference, okay? At every layer, what I usually do, or what we usually do in relaxed plan extraction is you have a set of subgoals, then you just, select actions achieving at least one of them, you remove those subgoals, and you can continue. Here there is a selection step. We select an action and the subset of goals. Okay, so that's the thing I pointed out before. For some reason, we have to make a selection step here. Now, why is that so? Like, can I not simply select all sub-goals that are achievable individually? Like, if you think about it, that's what you usually do. Like, when I can add a fact, if I can add a fact, that's fine. If I can add more facts, I just put them into the bargain and I don't lose anything. And this is not so here. Let me give an example. Say this is our sub-goal at the moment. These are the two conjunctions we want to achieve, okay? What this is really saying is you want to make P and A true, and you want to make P and B true. However, A and B are mutex, and our action achieves only P. So in principle, the action can achieve both subgoals together, right? I mean, I add part of those subgoals, so it's admissible to regress over them, and I can actually regress over both together. But if I do that, I get the unsolvable subgoal A and B, because I didn't make this part true, it becomes a subgoal. I didn't make this part true, it becomes a regress subgoal. Putting the two together, you get a new conjunction that wasn't there before. And that's exactly the point. So you get conjunctions that appear only due to a combination of subgoals you selected to support. Okay. I mean, basically, a cross-context condition, and also this concept was introduced by Patrick beforehand, is a new conjunction that arises not from any single conjunction you support with your action, but only from combinations of them, like from the leftovers of more than one conjunction you're choosing to support. Now, having said the word combinations, it's probably no surprise that the support selection problem is actually hard. So getting the cardinality maximal subset of conjunction subgoals you can support is a hard problem. Obviously, I'm not going to explain the proof. Now, the funny thing is, this problem has already been solved, even though it hasn't been stated in this particular form before. I mean, I presume Patrick had some kind of intuition along those lines. I don't know, it's certainly not been stated in this form before, but it's already been solved. The known solutions are as follows. Patrick's solution is enumerative. Like you have an NP-hard problem, you just sort of go through all possible solutions, if you will. I mean, sort of. The compilation actually makes explicitly not even just an iteration in time, but even in memory. You create the whole compilation and it enumerates all those possibilities. You might remember this paper, I don't know. It was actually best paper in 2012. What we did there is just provide a compilation that ignores those bad cross-context conditions, thanks to which we don't have the exponential blow-up, but of course we lose information. Finally, I'm not sure if you're aware of this, there was a paper in HK 2013 where they had something that, in my framework here, boils down to selecting only one sub-goal to support, which is a trivial approximation to the NPR problem, of course. Now, that we actually stated this NPR problem for what it is, we can do what we usually do. We approximate, right? How do you approximate this? Well, of course, you just take the subset maximal set of conjunctions. That's something you can do. You get a relaxed plan extraction procedure that's polynomial time and accounts for cross-context conditions. So this is the child of the marriage, if you will. Let's see the child of play, in other words, experiments. It's implemented on FD like everything. First of all, here's an efficient implementation of HC, which is a strict generalization of HM. So maybe Eris's, historically code can finally go to the garbage can. They're using exactly the same way of selecting the conjunctions that Emil Kida did, and just think that small x means few conjunctions, big X means many conjunctions. Type breaking is important. I want to compare this to Patrick's heuristic function, or Emil's heuristic function, really. And the two heuristic functions all necessarily have different implementations, so there's lots of arbitrary differences that you can't get rid of. So basically, applied all possible type breaking on both sides and checked what happened. We use those benchmarks. So here you see what happens when you have a very large set of conjunctions, okay, like the largest possible within 15 minutes. This here is states per second. Below the line is good. So what you see here is our heuristic function for large sets of conjunctions indeed is way faster than using the compilation. What you see here is, on the other hand, we're using a greedy approximation of the NPR problem, whereas the compilation is somewhat enumerative. So there is one could speculate that there's an information loss here, like an approximation loss, that we over-approximate, like overestimate the distance to go. Indeed, our initial state H values do tend to be a bit bigger. Like below the line here means our heuristic value for the initial state is bigger than that of the previous heuristic, of the compilation heuristic. But it seems fairly benign, and indeed the coverage is way better. Now, this is for large conjunction sets. The problem with that being they are not actually useful in practice. In practice, what works best, at least on the IPC benchmarks, are very small conjunction sets. So if you set x to 2, which is what Emil did in his experiments, because it was the best parameter setting he found, is that actually there's no real difference. The type breaking dominates it all. So for small sets of conjunctions, the two heuristics don't really differ. There are some exceptions to this, but let me get to the conclusion. So what's nice about this, I think it's a nice little contribution in the sense that, well, I at least understand now much better, what this compilation is actually doing. Also, we sort of subsume this thing that Emil did, because we can achieve the same complexity reduction without an information loss. Okay, empirically this works well, but as far as the IPC benchmarks are concerned, this is not really very important. So neither cross-context conditions nor large conjunctions that seem to be very important. Now, of course, it might be an artifact of our benchmarks. I don't know. But that's all I wanted to say. Thanks.